This is the Embedded System Design class, and today we will discuss the last talk, which is the data conversion. So um, uh, we will discuss some of the terms first: the analog to digital conversion, the digital to analog conversion, what's the sample period, the reference voltage, the resolution, the conversion time, and uh, after knowing the terms, we will move to the conversion equation. We will discuss this equation in details, and then we will move to the analog to digital conversion circuits. Namely, we will discuss two methods. The first one is the counter ramp, and the second one is the successive approximation. Once we are ready with the theory part, we will move to the BIC24 analog to digital module. We will touch how to the ADC of the BIC24 implement all of these, like the sampling conversion, the clock source, the reference voltage, the sampling, the conversion, and the analog input channels. So, in the subject of digital signal or processing, we have analog to digital converter, or in short, it's called ADC. It converts an input analog value to an output digital representation. This digital data is processed by a microprocessor, since it's digital now, and then it outputs whatever the processed value to the digital to analog converter to do the opposite operation that converts an input binary value to an output voltage. You can see it also here in the figure. We have an analog world. You can have any signal here. This signal will be continuous in its analog form, and then the analog to digital converter will convert this analog signal to a stream of bits. And then it will be ready for any microprocessor. In our case, our BIC24 microcontroller CPU. It will do the processing and generate the digital output. And then if it's needed to be given back to the system in the real world, then it is converted back to continuous analog signal using the DAC, or the digital analog converter. To understand how digitizing works, you could see here in this plot, we have a continuous signal in blue, and the amplitude of this signal is actually divided into several levels from 0 all the way to 7. So now we decided to have 8 levels, since 2 to the power of, let me change the color first. Since 2 to the power of 3 is equal to 8, then we need 3 bits to represent any digital value. So we should define a certain period. This would be called the sampling period, where we will sample this continuous signal periodically. This distance here should be the same all across the time axis. So now at this time, if we check the value of the continuous signal, we have to round its value to the nearest level. Here, the level is 1, and we represent it in 3 bits by 100, which will be digitized this way. Second one is right there, close to 2. So the digital value is 0, 10. Next, we have again 0, 10. Even if there are slight differences, we always round them. For example, this one here, this the sample is actually between level 3 and 4. So we chose to decide, or we decided that it's closer to 3 just by looking. If you know the exact value, then you can do the rounding precisely. And now we decided that it's going to be 110. That's the binary code for 3. And it could be even redrawn in digital format, like you have 0 here, followed by 1, followed by 1. Similar case for this digital signal and also for the digital signal. You can try it yourself for practice. Now, just some of the things to repeat and enforce. In the x-axis, which is actually the time, this time we call it the sampling period. In the y-axis, we have here the levels. This is the distance between two levels. And the number of levels, which is 8 in this case, is directly associated with the number of bits representing the digital signal. And from that, we will have the resolution idea. We will discuss it more in the coming slides. Here are some applications for digitizing. We have audio and speech recognition. Sometimes we use this for special effects, like the reverb, noise cancellation, etc. For the video, we could use filtering, special effects again, compression, and so on. Even as an application, we could use the digitizing for data logging as well. Again, we will formally define the terms or the vocabulary around this subject. So as we said, we have the analog to digital converter, ADC. It converts an analog signal, or usually this analog signal represented in voltage most of the time. It could be also in current. And we convert this analog signal to a digital value. For a DAC, or a digital to analog converter, it converts a digital value to an analog value. Now, the sampling period for the ADC, it's the time between each conversion. And we saw this in the x-axis, which was the time in the previous slide. And usually it's actually periodic, and we take this sample in a fixed rate. Now for the VREF, this is the reference voltage, which is the analog signal. Actually, the reference values, we get that because we know that the analog signal varies between two limits, between 0, that's a lower bound, and the VREF, and usually that's the upper bound. Sometimes we have in the lower bound minus VREF. So we have minus VREF in the lower bound all the way to the positive VREF. In our class, we will usually use from 0 to VREF. Now, for the resolution, we have the number of bits used for the conversion associated with the y-axis, which is the amplitude. So it could be 8 bits, 10 bits, 12 bits, 16 bits, etc. for different microcontrollers. In the previous example, we found out that the number of bits used were 3 bits. The conversion time is the time it takes for an analog to digital conversion to finish its job. That's the conversion time. Now, let's try to figure out the equation that is the important mathematical representation for an analog to digital converter. So to understand this, know that we have two axes, one for the analog and one for the digital. Again, the analog is starting from the lower bound, 0 volt, all the way to the upper bound, which is the V reference, the reference voltage. Now, for the digital part, we start based on the number of bits from 0 all to the way to 2 to the n minus 1. Now, if we have a point along this axis, which is Vn, it should be associated with the same distance in the digital axis. So this will be the output code. Notice that the distance to the lower bound is the same for the analog and for the digital. And you could say the same about the distance from that point to the upper bound as well. So the idea here is you are taking ratios and you are making that these ratios are the same. So if you take the ratio between the Vn and the Vref, that's Vn divided by Vref, then that's the same for the digital value. It would be the output code divided by 2 to the power of n. Notice here that we didn't use 2 to the power of n minus 1 because we know that we have digital value and the counts of these digital value start from 0 all the way to the 2 to the power of n minus 1, and the total digital points are 2 to the power of n. We cannot do the same here because it's continuous value. You can't count all. So now we know that Vn divided by Vref is equal to the output code divided by 2 to the power of, and there is a mapping this way. Now, this movement from analog to digital, that's the analog to digital conversion. That's the analog to digital conversion. So you want to find the output code. And to find the output code, you know that you multiply the Vn by 2 to the power of n and you divide by Vref, or you could say that it is equal to this ratio, which is Vn divided by Vref multiplied by 2 to the power of n. Since this is an output code, you should round this. There are many ways to round the number. We choose the simplest way in the microcontroller, which basically taking out the fraction altogether after the decimal point. So we are taking the floor. We are taking the floor. The reason it's very easy to implement in hardware. We just drop whatever value you have after the decimal point. Now, for the opposite way, or the other direction, if you want to convert from the output to from the digital to analog, that's the DAC, then you say that I'm interested in finding this value, which is the Vn. The Vn will be equal to this ratio, the output code divided by 2 to the power of n multiplied by Vref. Let's have examples to understand this better. That's an example. Here we decided that the Vref is 4 volts and the V input is 3 volt. And we want to find the output code. If there are 10 bits starting from the binary value of 0 all the way to the binary value of 1023. Notice that the limits here is actually 10 bits. So in binary, you would write them this way. For the 0, you would say 0, 0, 0, 0, 0, 0, 0, 0, and 0, 0. That's 10 bits. And for this upper bound, it's actually 1, 1, 1, 1, 1, 1, 1, 1, and 1, 1. Any other value in between, it will have some zeros and ones. So to get this value, you could say you follow the equation that we found. The output code would be Vn divided by Vref multiplied by 2 to the power of n. So it's 3/4 of 2 to the power of 10, or 1024. And then you get the floor. If you calculate this, the value that you will get is exactly 768. And that's the value of the output code. You can also find out the binary value for it. You convert from decimal to binary, and you would find that there are 10 bits here. In hexadecimal, it's represented this way, 0x 300 in hexadecimal. Now, let's have an example for the other way around. Here, we have the output code and we want to find the analog value. So for this output code, usually we have its binary value. We could convert it back to decimal, and you plug it in the our equation. Now the output code is 768 divided by 2 to the power of 10 multiplied by 4, and this will give you back the 3 volts. So now you have the analog equal to 3 volts. Since when we digitized, we didn't have any fraction, so we didn't lose any magnitude. When you convert back to analog, you get exactly the voltage that you begin with. Now let's have another example where you lose some of the fractions. Here, let's say that the Vn is equal to 2.17, and you want to find the output code. So if you plug in the values, the 2 to the power of 2.17 divided by 4, which is this 4, multiplied by 2 to the power of 10, and then you take the floor for this. This will result in 555.52. Now for this 52, we chose that we will round, we'll take the floor, we just drop it. So we will end up with 555, and we can find its binary value. We found its binary value, or this hexadecimal value. Now, when you do the other way around, which is doing the conversion from digital to analog, what happens is you will plug in the value, 555, you divide it by 2 to the power of 10, and then you multiply it by 4, and the result is actually 2.168. And you can see that we lost some value. In the previous slide, it was 2.17. That's the voltage that began with. So after we convert from analog to digital and back, this what we end up with. We lost some of the value here. So this is actually related to the resolution or the precision. So the levels is directly affecting the amount you are losing when you convert back and forth. If you want more resolution, you should increase the number of levels. So to understand the idea of the resolution, we will find it out for an n-bit ADC. We want to find out the smallest input voltage that can be resolved as one least significant bit. So it's like finding one step only, one step in the analog axis. So we try to find out if we have only one step in the digital, what is the corresponding analog voltage for that as well. You can also think about it in a different way. The difference between two consecutive digital value, you would try to find the difference in the analog that is associated with the digital value. So we found this out by applying this formula. One least significant bit voltage is actually 1 divided by 2 to the power of n multiplied by V reference plus minus V reference minus. The V reference minus or the VREF plus is the positive reference voltage. The VREF minus is the negative reference voltage. Now, we said that we will consider the VREF negative value 0. And for that, this equation in terms became the one least significant bit voltage is equal to 1 divided by 2 to the power of n multiplied by the VREF. Actually, we can get this exactly if we apply the rule that we have here. So we are actually interested in one least significant bit voltage. So if you want only one Vn, so you would say we have 1 divided by the VREF. Let me go back here. It's actually the other way around. So we know in the digital axis, we have 1. We want the value of 1 here in the output code. So you would say that it is 1 divided by 2 to the power of n. And then you multiply this by the vref to get actually the vn. So here you have the vref, you multiply it here. And the output code, you just replace it by 1 since you are interested in one least significant bit. And then you found the voltage corresponding to that single bit. That's the same equation that we found here. So as an example, if the VREF is equal to 4 volts and you have n equal to 4, meaning that you have 4-bit resolution, if you were asked what is the one least significant bit voltage, then it will be 1 divided by 2 to the power of 4 multiplied by 4 volt, which is equal to 1 divided by 16 multiplied by 4 volt, which is the 0.25 volt. Meaning, if you start from 0, 0, 0, 0, all the way to 1, 1, 1, 1, you will have 16 level. Each level, so moving from 0, 0, 0, 0 to 1, 0, 0, 0, the next level directly, this will correspond to only 0.25 volt. Another, if you have 4 more, you will have 1 volt. Again, 4 more, another volt. Again, 4 more, another volt. And the last 4, you have the last voltage, and the total number of voltage you will have 4 volt. That's the idea here. Let's have it in the same thing. Now you see the difference here. If you consider the output code 768 and 769, you see that the difference between them is just 1 level. You can see it here in the low significant bit, or the least significant bit here. So 1 least significant bit voltage is 1 over 2 to the power of n multiplied by VREF, which is 1 divided by 1024 multiplied by 4. And if you get this, it will be 0.0039 voltage. So starting from 0, moving to the next level, you will add up this amount of voltage, and so on and so on. If you reach to this, which is 768, and you want to go to the next level, which is 769. Now, if you calculate the analog value for each one of them, you will find out that this value, this is the one that we got at the beginning, that's 3 volts. And the next one is 3.0039, which is the one least significant bit voltage. So at this point, we have these equations. That's what I'm trying to put everything all together. So the Vn is the input voltage, the Vref plus is the reference voltage, the Vref minus we consider it to be 0 volt, and n will be the number of bit of precision or resolution. Now the output code is equal to the Vn divided by the Vref multiplied by 2 to the power n, that we take the floor. The Vn is equal to the output code divided by 2 to the power of n multiplied by the Vref, and we also can find the one least significant bit voltage by finding out 1 divided by 2 to the power of n multiplied by Vref, as we explained in the previous few slides. Now, these 3 equations is actually only one ratio that we equalize to each other from the analog side and the digital side, and we formulate these 3 equations based on that. As a hardware, you will have an analog digital converter block like this. You should apply a reference voltage here, and you give the analog voltage as an input, and the ADC will work whatever hardware related to these equations inside this block and give you the output code ready. So you don't have to calculate this. You just plug in the voltage in the input, and the ADC will do its magic and output the code for you. Now, we said magic, but now we know the mathematics behind it, so it's basically clear to us. As example, that's more examples here. We have the V reference is equal to 5 volt, and the input voltage is 1.46 volt. If you are asked to find the 10-bit analog to digital output code and the 12-bit output code as well, then for the 10 bits, you take the ratio, which is the Vn divided by the Vref, and we know that's 1.46 divided by 5 in both of them, in the 10 bits and the 12. One time you will multiply it by 2 to the power of 10. That's your resolution, the 10-bit output code. And the other time you will multiply it by 2 to the power of 12 or 4096. And based on this, you can get the decimal value. Based on this calculation, you convert it to binary and you can generate the hexadecimal for each one of them. Now, let's have more examples. If Vref is 5 volt and the 10-bit analog to digital output code is this value, so we know the output code. What is the ADC input voltage? Plug in the values. We have 0x A to 1 divided by 2 to the power of 10 multiplied by 5. Now this value, we can generate the decimal value for it, which is 298. And then we calculate. And by calculation, we found that the input voltage is actually 1.46 volt. Another example, if the Vref is 4 volt and you have an 8-bit analog to digital input voltage, and this input voltage is corresponding to 2.335 volt, what is the ADC output code? Again, plug in the values, the analog divided by the analog, 2.35 divided by 4, and then you multiply it by 2 to the power of the resolution, that's 8, n is equal to 8, 2 to the power of 8 is 256, and you find this value here. You get the floor, which is, you have 150.4, you get the floor and you take out the 4, and now you have 150. In hexadecimal, it's 0x69. And that's the way this equation works. Now, after having or discussing the terminologies, discussing the equation, and how to convert from analog to digital and digital to analog mathematically, how to represent this in hardware, how to represent this idea in hardware. So this representation is based on something you probably have taken in one of the data structure courses, which is the linear search and binary search. To just remind you about the idea here, for the linear search, let's say you want to find the letter J in a sorted list, which is A, from A all the way to Z. Me and you, we are human beings, we have our brain, we can pinpoint the J right away. But for a computer to find it among a list, it starts looking at the beginning and then move and check, is J equal to A? No. Move to the next one. Is it equal to B? No, and so on. So it hops 10 times, about 10 times until it finds the value of J. So let's say that the searches or the comparison that the software or hardware must do to reach to the solution using a linear search for the letter J is only 10. Now, for the binary search, again, you try to find the same letter J, but now what you do in binary, you would say, okay, I start here at the beginning. I jump to the middle point or the midpoint of the list, which is, if you say that it's 16 letters, the 26 letters, then you jump to the middle point, which is 13. And now you compare the J to the M. You know the J comes before them. So you jump back, but now you jump half the length of the list from 1 to 13. And we decided that the half is 6. And now you compare the F to the J. You know it comes after the F. Now you jump again half and you pinpoint the J. So for J, we had to do 3 comparisons. 1, 2, and 3. If you compare 10 comparison to 3 comparison, you know that the binary search is actually more efficient. If you want to find it like in a worst case scenario, in the linear search, the worst case is you start at the beginning and the letter that you want to find is Z. So you have to go through all the list doing comparison 26 times. For the binary search, the worst case is actually a log to the base 2 of the 26. So you can see that if you can calculate this value, you will find that value is actually much less than the linear search. And that's why binary search is famous and is used in many applications. Now, to see the hardware, first I need to introduce to you the comparator. The analog comparator compares two analog voltage. You have an output this way, and you have two analog inputs, one in the plus and one in the minus. So we have Vn plus and Vn minus. Now the output is 1 if Vn plus is larger than Vn minus. It's going to be 0 the other way. Now in the big 24, it's actually in the big 24, it has the two comparator, which is makes it a very simple or make the analog digital converter very simple. Here's an example to understand how is this working. Now let's say that the dotted line is Vn minus and the solid line is Vn plus. So you always subtract this value from you do the comparison between the Vn plus and the Vn minus. Now here we see that the Vn plus is less than the Vn minus, so we have the value 0. It always here in this place, it's always less than that, so we have it as 0. Similarly here and here, so we have it 0, and as well here, so it's actually 0. For the other region, which is this region, and this region is actually 1, because Vn plus is larger than this dotted line, which is the Vn minus. And you can see there is a problem here in this dot where the Vn plus and the Vn minus are very comparable to their value. So here we have the edge, and actually this is problem in analog. You could have fluctuation or things like that, but for this is actually outside of the scope of this lecture, so we will leave it for another electrical maybe course. The idea here is to do the comparison, and the output becomes either 0 or 1 based on the comparison. Now, to use the ADC, this is the first method, which is associated with the linear search. The linear search. This is called a counter ramp. And here we want to implement the ADC. So what happens is you have the comparison, and be careful here. It's the other way around. The plus is in the lower part and the minus in the upper part. So you input the input voltage here in the plus, and you compare it with a negative, the value that comes in the Vn minus. Initially, you have a counter here in this block, and hence the name counter ramp. It starts from 0, and it starts counting 0, 1, 2, step by step linearly, until you found the value that is associated with the Vn. So here you count. You have a counter. You can implement a counter in hardware, and you get the value of the counter either in parallel or serial. It's up to you. And also, this value is given to a digital to analog converter to convert the digital value here back to analog as well. So for the digital to analog voltage, or from digital to analog converter, it needs a reference voltage. Now, the idea here, now you can compare the output that you just, at the beginning, you started from 0. So this value would be equal to 0. And you compare the input to 0. Now, if the VDAC is still lower than the input voltage, you redo this and you keep redoing this until the VDAC becomes larger than the V input. And now you know that you reach to the digital value. To see this in the diagram, you start with 0. This is the RAM that you see here. This is the output of the VDAC. And you go step by step because you have a digital value and you convert it back to analog. So now you have the VDAC and you can use the comparator. Both of them are analog now. And compare the VN, the value of VN that you know, you can convert it to digital by the comparison. So here we started with 0. No, doesn't work. 1, 2, 3, 4, and you keep counting until you reach to this value, which is 8. And now for the next count, the counter increase by 1, so it becomes 9. So now you have 1, 0, 0, 1. And you convert it back to analog, which is the voltage, 9 volt. You compare this to the VN. You found out the 9 voltage is larger than the VN at this time. And you know that 1001 is actually the digital value, and you output that in whatever format you want, whether parallel or serial. So it's like a guess game. Guess my voltage. Is it 1? Is it 0? Is it 1? Is it 2? You start counting. The control logic uses the counter to apply successive codes one by one to the DAC until the DAC output is greater than the VN. Once it's greater, you know that you reach to the digital code. Now this is slow. We know that because it's linear, and have allocate the worst case time for each conversion, which is 2 to the power of n clock cycle for an n-bit ADC. So if you have 4 bits, the 2 to the power of 4, 16, and the worst case is checking 16 times, as we've discussed in the linear search. Now, the other idea is the successive approximation. The successive approximation. And the idea here, if you compare the hardware between this and that, you would see that it's kind of the same. The only difference is what's going on inside this box. What we do is successive approximation control logic. So in the figure here, we know that we will, or we want digital code, and this digital code is 4-bit. We know that it's 4-bit. So what we do, starting from the most significant bit, we get the appropriate level, either it's 0 or 1, and then we move to the next bit, moving from the most to the least, and then we go to the next bit, and then we end up with the last bit. You can see we have only 4 steps, which is log to the value of 2 to the power of 4 to the base 2, and this value is actually 4 compared to 16 in the counter ramp. So the successive approximation is more efficient. Now, to understand the idea behind this, we initially set the VDAC to half the VREF. Notice that we go to the half point for the VDAC and then compare. See if the VN higher or lower than the VDAC. If VN is higher than the VDAC, which is half a VREF at this point, then the next guess is between VREF, which is the upper portion, between VREF and half the VREF. Else, we get the next from half the VREF, from whatever value to the ground. And we keep doing this. So you do this for each bit. You know that it's 4 bits, so you do it 4 times. and it would take n clock cycles. So here 2 to the power of n, our n is equal to 4 in this example. To understand this better, let's detail every step in an example. Let's say that you are given a 4-bit successive approximation, and the reference voltage is 4 voltage. And let's say that your analog value is actually pi, which is 3.1459 volts. Now, at the beginning, you clear the DAC, you make the value 0, 0, 0, 0, and we know that the VDAC is equal to your guess divided by 2 to the power of n multiplied by the VREF. And we know how to calculate this mathematically. Now you guess the most significant bit first, all the way to the least significant bit. You guess it to be 1 and check if this guess is okay or not. Now, if you guess this value, the value or the DAC value would be 8, and the V or the analog voltage of 8, the VDAC is 8 divided by 16 multiplied by 4, and that's 2 volts. Now, compare your value, you know, it's 3, you know, it's pi. Pi is larger than 2 volts. So you're guessing for 1, since it's larger, is a correct or was a correct guess, and you keep this 1. And now you move to the next bit and you guess it to be 1. From that, the voltage, the digital value is 12, and the analog value corresponding to 12 divided by 16 times 4 is 3 volts, and you compare, actually this is 3 volts here, you compare pi to 3, again it's larger, so your guess is still correct. And the DAC input at this point is 0011. You go back again, you guess for the next bit, and your guess here is 1, and check if this guess is okay or not. The value is 14 divided by 16 multiplied by 4. Now it's 3.5, which is larger than the pi value. So your guessing for 1 was incorrect, and you should roll it back and make it 0. Now you work with the next bit, you make it 1. The value is 13. Do the calculation again, it's 3.25. And you compare the pi with the 3.25, still larger. So your 1 guessing was wrong, and you roll back again to this value. And at this point, you did 4 steps, and you know that it's actually the correct digital code for this analog value. I visualize this as well. But actually, before I visualize, I can check the result right away. You know, you can apply your mathematical formula. The output code is Vn divided by REF multiplied by 2 to the power of n. 3.14159 divided by 4 multiplied by 16 is 12.57. You take out the fraction and you bring it to 12, which is the same value. But the hardware cannot do this. We should have a very simple hardware instead of having a hardware that do this calculation. So this simple hardware would use the successive approximation for the analog to digital converter. This one, initially you didn't pick anything. You start with guessing 1. So this is, you are not even going to consider it. So you start with this, and now you get the value. This value is it less or larger compared to the voltage? So here we know that the voltage is larger. So now you know 1 is correct, and you guess the other one. Here, if it is 1, and here it is 0, this is what you test. If it is less than or larger than, you know at this point that this one is correct, and you move to 1 and 0 for the next bit, and you do the comparison for these 2 values. You know that this one is correct from the 3rd step, and then you move. Now you know that these 3 values are correct, and you guess the last bit, and from the comparison you know this one is correct. You can see that we have 4 stages: 1, 2, 3, and 4. Now for the commercial ADC, there is a key timing parameter, which is the conversion time. we should be aware that the conversion time is very important, and this is why we should choose the successive approximation. The conversion time is how long does it take to produce a digital output once a conversion is started. It's up to 16-bit ADC. There are actually up to 16-bit ADC available. So you can have maybe 8 bits or 10 bits or 12 bits or 16 bits. That's the common resolution. It's separated into fast, medium, and low speed families. The serial interfaces are common on medium and low speed ADC. And for high precision ADCs, the challenge is to keep the system noise free from affecting the conversion. Now, assume a 16-bit DAC and 4.1 voltage reference, then the one least significant bit corresponding voltage is 4.1 divided by 2 to the power of 16, which is 62 microvolt. So the slight noise can move you from one level to the next. So you should be careful. If you increase the resolution, there is the noise factor is coming to the picture, and you need to be aware of it. Now let's move from the theory part to the PIC24 analog to digital converter. Now here are the choices for the PIC24. It uses the successive approximation, which is obvious. If you go to the PIC24 Venn diagram, you would see analog value, and we've mentioned that when we talked about the GPU. You have AN0, AN1, AN2, 3, 4, and 5. 6, 7, and 8, you won't find them. And then you have 9, 10, 11, and 12. That's for this specific PIC24, which is PIC24 HG32 G202 or GB202. So you have two resolutions here. Either you choose 10-bit resolutions or 12-bit resolution. Now, if you choose 10-bit resolution, that's the default. You have up to 13 analog inputs, meaning starting from AN0 all the way to AN12. However, in this family, these two families, or PIC24 HG128 and 32 specific, AN6, 7, and 8, they don't exist. So you don't have actually 13, you have only 10 different input pins. To understand this better, you could plug in here an analog value that get the analog temperature of the certain surface. Here you maybe calculate the humidity. And the other bin, you calculate something different, maybe the air pressure, and so on. There are so many examples of analog values that you are interested in. Each one of them is 10-bit resolution. So you have 10 analog bits or 10 analog bins, and each one of them has 10-bit resolution. Now, the 10-bit resolution, it can actually simultaneously samples up to 4 analog inputs or 4 channels at the same clock cycle. So you enter 4 of them in one go. That's what we mean by the 4 channels here, or the 4 simultaneous channeling. This is only available in the 10-bit resolution. In the 12-bit resolution, there is no simultaneous sampling. You have only one channel at a certain clock cycle. But this is okay. Like if you are measuring the temperature and humidity, and when you were measuring them, the difference between taking the value of the temperature and the humidity was 1 clock cycle, which is fraction of a microsecond, then you should be fine. It's not a big deal. Now, the reference voltage is VDD, or it could be a separate voltage. Now, if we choose a separate voltage, then we can use AVSS. And you can have the minimum value of the AVSS and you add to that 2.7. So if we have 3.3 and like this is the VDD of the big 24 and you add 2.7, you would end up with the voltage, which is 6 volts. That's the voltage that you can have. And that's normal. Like you have no idea what is the reference voltage that you are dealing with as an analog signal. So you should have it more than 3.3 volt. It could have multiple inputs, more than one input channel, when that's obvious. You can see the ANs here. And now for the clock source of the ADC, you have two sources. Either you have it a divided frequency of oscillation, and in this case, the ADC clock period, or what we will call TAD, for T analog to digital conversion, or analog to digital, TAD cannot be less than 76 nanosecond for a 10-bit mode, or 11 or 118 nanosecond for 12-bit mode. So the idea here, you get the frequency of oscillation that you get. You remember the oscillation module. You got the FOST, and it is divided in a certain way. That's the first option. The second option is internally generated clock. This internally generated clock within the ADC module itself. It's outside the oscillator module, and it's actually inside the ADC module. This internally generated clock is generated while you're designing the ADC, so they try to get the appropriate clock that works with it. And the period for us is fixed to 150 nanosecond, or in frequency, it's 4 megahertz. And the obvious choice for you is the internally generated clock. They actually did that to fit the ADC operation. But you still have the other choice. In case this is not right for your application, you have the other choice. We will go more into this point in the next few slides. So now for the sampling and the conversion sequence, we have the sample time. That's the total time for everything. Now we have sample time and the conversion time. The sampling, the input voltage signal is connected to the sampling capacitor. So we have a capacitor here, and whatever comparator you have, you convert the input with whatever comes in the feedback and check. You store the output of the comparison, which is going to be either 0 on 1 or 1 in a capacitor. So it's connected here. This switch is connected at the sampling time. Now, in the conversion time, this switch will be open. So now we don't have this anymore. And then it's fed to the successive approximation analog to digital converter for calculation. This is what we mean by sampling and conversion. So the sampling, the input voltage signal is connected to the capacitor, and in the converter, the input voltage signal is disconnected from the sampling capacitor, and the stored value in the capacitor is converted to digital bit using the successive approximation method, or the SAR. That's the idea of the sample and conversion. Sometimes we call this sample and hold. Sample and hold. So to choose channels, remember we have from AN0 all the way to AN12. We have a comparator here. You can have any analog signal from the outside world, and you choose whatever you have, and you connect it to the plus, to the plus pin. The selector here is called the channel 0 selector, and it selects the analog from AN0, AN1, AN2, all the way to AN6, the AN12, and be aware that 6, 7, and 8 are not there. And now for the negative, you have only two choices. either you choose AN1 or you would choose the VREF low, which will be connected to ground as we specified earlier. And here you have the channel 0 negative value selector that select between these values, and you can connect it to the negative. Now you work out the comparator in the same way that we described here. You have this analog to digital converter, or sorry, you have this comparator connected to capacitor and then to the successive approximation ADC. Here we have the comparator and the switch and the capacitor, and it goes to the successive approximation ADC. Here, this step is sometimes called sample and hold, as we specified earlier. Now, after understanding this, we can look at the full picture. This is the block diagram for the VIC-24, HG128GB202. You can see that what we discussed earlier, here you have the comparator, you have the sample and hold, and then you have it here inside the successive approximation ADC. You can see that you have up to 4 channels that you can do in parallel. You can do that if you use 10-bit resolution. If you use 212, then you can choose only one channel, which is channel 0. This is the first channel, channel 0. This is channel 1, channel 2, and channel 3. These are the 4 channels. If you use 12, you must use channel 0 and channel 0 on. There are many details here, but the idea is the same. You have so many multiplexers, so many choices. We made it simpler for you to understand. You have here AN0 all the way to AN12, and you can choose between them. And here you have AN1 and the V reference low, and usually you have V reference low right there. Now for the next channel, you don't have all of the analog signals from 0 to 12 here. You have only from analog, you have 2 on, AN0 and AN3, that's it. For the next one, you have AN1 and AN4. For the next one, you have AN2 and AN5. Now for the minus, you would choose from between the low and AN9. Here, you choose between the low and AN10, and here you choose between AN11 and the VREF low. This is actually architecture choices, and looking at it in a different way, you could see that they say, okay, for channel 0, you have everything that you can choose from. So if you choose 12 bits, I should give you all the possible options. And for the other one, you have from AN1 to the V reference. Look, that's the choice that they made. For the other 3 channels that you can use, and probably if you want to use 10 bits, then you have you can simultaneously read 4 channels. This is the options. You have 0. Look at the counting here. We have 0, 1, 2, 3, 4, 5, 6, 7, and 8 are not there. 9, and 10, and 11. This is the way we distribute. Now, once you have the channel or the analog right there, the successive approximation works. And this is the critical part here. The result that you can access in the programming is actually in the ADC1 buffer 0. So whatever digital value you are generated, you can read it here. So you just give the voltage, you make the choices properly. So there must be special function register that can help you with making these choices. Choose, for example, 10 bits, single channel, that's channel 0. Choose some of the things or some of the fields that make the sampling and holding appropriate for your application. And once you're done with the special function register, the digitizing happens, and you have the value right there. You don't calculate anything. You don't plug any equations in the code. That's the idea of this. Of course, for the successive approximation ADC, we have some choices for the VREF and the high and the VREF of the low. There are so many options here. and we will discuss the special function register of this option soon. Now, let's move to the time for sample and convert. And we will check this by a simple equation. The total analog to digital conversion time is equal to the sample time plus the conversion time. So the sampling looks at the input voltage and uses a storage capacitor to acquire the input, as we explained. Now, this time is configurable up to 31 clock TAD periods. So you can choose the appropriate amount of clocks for the sampling based on your application. So once you choose that for the sampling, that's the sample time, and you can choose whatever N you decide based again on a special function register. You multiply that by TAD. Now you're done with the sample time. Now the total AD time for converting a single reading, you have a single digital reading, and the total time for it, you will have, if you take 31 clock, you take the maximum, the 31 sample clock, you have it here for the sample time. And then you will have 12 clock for each bit in the conversion time if you choose 12 bit. If you choose 10 bit, then you will have 10 TAD. So if we choose 12 bits, you have 12 clock for each bit, and then 2 extra overhead clock periods. So the total time would be, that's an example only, 31 sampling if you choose N to be 31. If you choose 12-bit, then that's 12. And then you add 2 extra overhead to run through this hardware. You can see it's kind of complex. And the total is 45 clock periods now. You calculated the periods, which is N. And you add to that 12 plus 2, and you multiply all of them with TA. So if you use an internal clock, you know that it's 4 meg or 250 nanosecond. So one maximum AD time conversion from the input of the analog value or the reading, that if you have a single reading, you would take 250 nanosecond multiplied by 45 clock cycle, which is going to be 11.25 microsecond. You can see that it's very short in terms of time. So if you choose 12, as this example suggested, it's fine. You can do one sample, and then you wait for this time, and you do for another sample, and each one of them will have this time. You can also convert it to frequency. The frequency of sampling would be this frequency. Now we will discuss the special function register. You would see in the analog to digital converter, there's so many special function register. At this point, we are ready to discuss each one of them. We actually have this first special function register, which is the AD1 control register 1. It has 16 bits, and as you can see, it's from 0 to 15. And this table details all the fields. The first one is actually the done, and this is the conversion status bit. It's a single bit. If it is 0, it means that it's not started or in progress. Usually it's in progress, so the conversion from analog to digital still in progress. And if it is equal to 1, then the conversion completed. So you should check this bit to decide if the conversion is completed or not yet. The next bit is called SAMP, or the sampling, the sample enable bit. Do you enable it or not? Remember, this is an analog signal. If, for example, you are trying to measure the temperature, you don't want to sample every few microseconds. You probably need to wait for some times. So you could have the sampling active all the time. So you sample very frequent, or you make the sampling, you make it stopped. So for this enable bit, if it is 0, the sample is stopped, or you are holding the value. If it is 1, then the sample is actually active. This field bit, to understand it better, it's actually associated with the next one. So the next one is the auto sample bit. I represent it by this arrow, the purple arrow. If it is 0, then you have a manual sampling. If it is 1, then the sample begins immediately after the last conversion. Remember, you have sample and then conversion, sample and then conversion. So if you go to the beginning, the sampling here, it will start right after the conversion that was before that. So this is why what do we mean by auto sampling? So once you finish the conversion, the next sample starts automatically. Again, sample and conversion for the next analog input reading. And then automatically you move to the next, automatically you move to the next, and so on. This is if you choose auto sample. So if it is 1, that's auto sampling. Sample begins immediately after the last conversion. If it is 0, you don't do it automatically. It is actually manual sampling. Now, to do the manual sampling, you use this bit. If it is 0, you don't sample. If it is 1, you sample. I think it's clarified. The idea is clarified now. Now, for the next 3 bits, which is the SSRC, this is the sample clock source select bit. And if it is 000, it's actually manual. This is supposed to be 000 if you use manual. If you use 111, then you use auto convert, which is the red arrow. Auto convert is like the idea of the auto sample. Once you finish the sample time, you automatically move to the conversion time. And that's actually the obvious choice. If you want to do directly after you sample, you go to the conversion, you should make this value 1, 1, and 1. If not, for any reason, in all the applications that I've done, I always use autoconvert. But for any reason, if you want to have some times or it, you can make it manual. Now, after that, there are obvious fields that you need to deal with. One of them is the form of the output. If it is 00, it's unsigned. If it is 10, it's a signed value. It depends on the format that you want in the output. Remember, this will be a digital output. So do you care about the most significant bit? Is it the sign or not? Do you want a signed value or unsigned value? Unsigned is 00, signed is 10. So let's say you are measuring a temperature value for a certain surface, and the temperature could go below 0, and you want negative value. At this point, you would use signed value, which is 1 and 0. If you are measuring the temperature and you know that this surface is usually super hot, it is never cold, then you don't use signed value, you use unsigned. And there are many, many examples for this point. The next field is the AD12 bits, which is the selection between 10 and 10 bits. That's the resolution. If it is 0, you choose 10 bits, which you can have 4 channels simultaneously. If it is 1, that's 12 bits, and you use only 1 channel, which is channel 0. Now, the most significant bit, as usual, is the on and off bit. So if it is 0, then the analog then the ADC is off. If it is 1, then the ADC is 1. That's the AD1 control register number 1. We have another 2 special function registers that are called AD1 control register number 2 and AD1 control register number 3. Now for this special function register, the control register number 2, it has 2 fields actually. One of them is the channel selector. It has 2 bits. If you use 00, you will use only channel 0. If it is 1, 0, you have two channels, channel 0 and channel 1. And if it is X, meaning don't care, and 1, you convert 4 channels simultaneously. Now, we usually will use in all our application only a single channel, channel 0. So at this point, we can say that for this bit, we will assume bit 8 and 9 equal to 0 and 0 for this control register. Now for the 3 bits from 13 to 15, that's 3 bits. This is the converter voltage reference. And this is actually what we talked about here in the block diagram. And we said that we will talk about it more. So the choices here is for the AD reference voltage plus and minus. If you choose zeros, then you have a VDD and a VSS bins, and you have other options as you can see in the table. In our case, in all of our application, we would use 0, 0, 0, which is this option. So we use this option and we use always channel 0. From this discussion, you know that the analog to digital 1 control register number 2, the value for it in all of our application is 0x0000. So it's zeros and you're done with this control register. Now for the next control register, which is the AD1 control register number 3, this is basically for the frequency, for the choice of the TAD. That's the clock cycle TAD. Remember the discussion that we had before here? We said that we will choose n, and we could choose 12 or 10, and then you multiply everything by the TAD, whether it's in the sample time or the conversion time. How to specify these numbers, for example, this n, we can use what you see here. So we have I will start from the most significant. We have the ADRC, which is the clock source select. If it is 0, then the clock derived from the system clock, which is FCY. If it is 1, then the ADC internal RC clock is chosen, which is the 4 mega. You can see this also here. Here you have the most significant bit of this third special function register for the ADC. If it is 0, then you use the TOSC or the FOSA, you could say. And from that, you could convert it to FCY if you divide it by 2. Or if you use the TOSC, then you multiply it by 2. Remember the relation between the frequency and the time. And you get the TCY. And from the TCY, you can see this block. If you choose here 0, from the TCY, you can use the AD1 control register number 3 from 0 to 7, which is this part here. You see it here in red. You could use this one for specifying the ADC conversion, the clock multiplier. And you have from 1 all the way to 64. Now for this one, the ADCS, you have the TAD conversion clock when the ADRC is equal to 0, meaning this choice. Now the TCY, which is this TCY factor, is the ADCS07, which is this one, plus 1. So the TAD would have this vector value, and you multiply it by TCY. And that's what we want. What we are interested on is the TAD. And the TAD is this factor, which is this value, but you add 1 to it. And then you multiply it by whatever TCY you have. Now you have 8 bits. And notice the options that you have. Even though you have 8 bits, that's 2 to the power of 8, which is 256. But you use only the least significant 6 bits of them. These 2 most significant bits are always 0. This is to match different family of the big 24. now here, if you use 0, 0, 0, 0, 0, 0, then you can say that the value is actually 0 multiplied by TCY. This is why we add 1. So for this one, we use 1 TCY. For the next one, 2 TCY, that's the TAD. For the next one, 3 TCY, all the way to 64 TCY. So that's basically the value of the TAD for each choice of these 8 bits. Now that's the first option. And we said that this is the, that comes actually from the oscillator module. Since you get the FOSC from the oscillator module, that's one choice. And the easiest and the most reliable choice is the ADC internal RC clock that is inside the analog to digital converter. And this one has a sampling time already fixed, 250 nanosecond, or the frequency is 44 meg. That's the other option of the clock source to facilitate the ADC operation. Now we need to explain one field, which is the SAMC. It has 5 bits, and that's the auto sample time. The auto sample time. Now, this automatic sample time is associated with the SSRC. If you remember the SSRC that we talked about here. Now, the obvious choice that I said is to have an auto convert, which is 111. Now, for the sampling time, the auto sampling time, this time here, for the conversion time, it's obvious. Whatever choice you make, 10 or 12, based on this bit. So this bit tells you the value here. So we're done with this one. It's easy. For this one, also easy. The sample time, you can specify it if you use automatic sample for the SSRC. If it is 111, then you can find this value n by choosing one of these options from 0 all the way to 31. The maximum, when you choose 11111, then this n is equal to 31. So this is a very important field if you want to calculate the sample time. Now, once you decide or specify all the special function register for the analog to digital converter, we can look more at this figure. Now, the automatic sampling and the automatic conversion mode, the auto sample time, or the SAMC, bit in the control register number 3, select from 0 to 31 ADC clock cycles, or the TAD. So if you choose a certain value, you can plug it in here, and the sample time would be n multiplied by the TAD when this switch is closed, when you are sampling. When you are holding, you're talking about the conversion time based on the number of or the resolution that you chose, either 12 or 10 bits. And then you repeat this for the next cycle and so on. It's detailed here. In one here, the samples start automatically after the conversion. So it is, we actually make this automatic. For number 2, which is here, conversion start automatically, which is basically the auto conversion. So that's auto conversion here. And we have here auto sampling. The third here clock, we sample again. We repeat this process for the next analog reading. And we explain the same idea actually here with colors as well. So now for the last special function register, which is the AD1 channel selector. We have 2 fields on it. One of them is the analog input channel channel selection, That's channel 0 SA, or selection of the analog value. So you have here 5 bits. Actually, you don't use the most significant bit here. We only use these 4. And you have from AN0 to AN12, whatever choice you want. And it's associated actually with the value itself. So if it is 0, then all zeros. If it is 12, it's 0, 0, 1, 1, 0, and so on. Remember, 6 and 7 and 8 are not there in the Venn diagram, so you cannot use them. Now, for the negative input, or the negative analog input, you have either 0 or 1. If it is 0, then you use the VREF, which is usually connected to the ground. If it is 1, then you use a negative input that is connected to AN1. That's for the 2 selectors. So for this special function register, you just specify the selections for these values. Now, how to do or configure the ADC, you need to specify the values of these 4 special function registers. The first control register, the second control register, the third control register, and this register. Some of them are very easy. This one is very easy. You just decide which channel that you want to use. This one is always connected to ground, so you don't have to worry about it. For this one is actually all the time 0x0000 based on our discussion. Now, the third control register for the calculation of the TAD and for this sampling time calculation. And the first one is, it has a lot of options: the auto sampling, the auto conversion, the form, the selection of the bits, and 2 bits, one of them a status bit, and one of them to turn the ADC on and off. So to configure the ADC, you need to specify all of them. It's only listed here. The only thing that is that you need to remember is you have actually the AD1 BCFG high and the AD1 BCFG low. These are actually 2 special function register that lists the BCFG values. We use only this one for the big 24, since we have from BCFG 0 all the way to 12 and nothing more, so we don't use this one. And other than that, you just need to configure control register number 2, 3. You choose the BCFGs that you need to work on. So if you want to, let's say that you want to use AN2, then this value should be equal to 0 now. Remember, before this lecture, we always make this value equal to 1. Now, if we want to use an analog value, we make it equal to 0. Other than that, specify the control register, 2, 3, 1, and then the last step, turn the ADC on. Now, to understand the whole idea of the analog to digital conversion, let's see some application first, and then we will solve some problem. One of the applications is the potentiometer. You can see it here in this picture. It's actually what we call a knob that you can move. You can maybe see this in old radios where you can increase the volume or decrease the volume or change the channel, things like this. Anyway, the idea here, you have 3 pins. One of them is connected to the ground. The other is connected to the VDD. And here you have a variable resistance input. So you tie the outer 2 legs to the VDD and the ground, and the voltage in the middle leg will vary between the VDD and the ground as a variable resistance. Now you change the position on the wiper on the resistor here, and based on that, you can increase or decrease this resistance. Now you can change, since you're changing the resistance, you know ohm law, which is the voltage is equal to the IR. If the voltage is fixed, and you are changing the resistance, then the current will change based on that. And you can do the same with whatever parameters of the Ohm law that you are fixing. Now, in this example, what we did, or you were asked to design a system that reads an analog input from the potentiometer and display its corresponding value using the LEDs. That's it. Read it and display it. To do this, we need to do interfacing and program. So for the interfacing, this is basically, we choose RB board from RB0 all the way to RB15. So that's 16 bits that we can choose from. And we have only two choices, either 10 bits or 12 bits. That's the resolution choices that we have. Here we choose from 0 to 11. You see that they are connected to LEDs. And then after the LEDs, we have resistance. So we actually chose 12 bits in the connection of the port B. We have the minimum connection. We discussed this before. We have the master clear. You have the VSS. Now for the AVDD, we connect it to the voltage source. The AVSS, it's on the ground. Now, if we choose control register number 2 to be 0x0000, then we will use these values, the VDD and the ground, and we're done. Other than that, we will use the potentiometer here. Sometimes it's called potentiometer. And we connect it to we connect the three terminals. This is VDD and this is ground. And this one here, the variable resistance, is connected as one analog signals, and you have the choices from AN0 to AN12. These are the choices that you have. Again, 6, 7, and 8 are not available. We chose AN0. Now, after we did the interface, so basically the only new thing here in the interface is that we specified the analog input, and that's it. Now, for the coding, we have the ADC. You can configure ADC1. And it accepts an argument, which is the ANX. So in our example, we should give it AN0. Or simply, since this is unsigned integer 8, we just give it the value 0, indicating that we are using AN0. And then we configure the control registers, or the special function register. Control 1, control 2, control 3, and we use the channel selectors. Once we're done, we switch it on. We switch the special function or the analog to digital converter on. That's the idea. So let's start by the easy ones. The control register number 2, as you can see, they are all zeros. The channel selector is whatever you have in the arguments. So for this example, since we tie it to AN0, we should put 0 here, and it will in turn be transferred to this value for the AD1 channel selector 0. You can see the choices here and here is based on the application that we have. Notice that the application is simply saying, okay, whatever you have value in the potentiometer, display it, and the LEDs, and that's it. It didn't specify anything. That's your job as an engineer to choose the obvious or the correct choices. Some of them, it's whatever you want. So originally, we will have the module off. So the most significant bit here is 0, and that's what we have here. We use 12 bits. This is why we have 1 here for this bit. We use digital output format, which is unsigned, since this potentiometer doesn't have negative value. So we choose 0, 0. And we will have auto conversion using internal counter. since you have an auto conversion, that's the choice that you make here, 1, 1, 1. And the obvious choice for the sampling, remember, this is analog signal. And the potentiometer, you move it mechanically using your hand. So there is no point for sampling automatically. Like you have, you sample hundreds, maybe thousands of sample per a millisecond. There won't be somebody who's that fast changing the potentiometer mechanically. Even for any other analog signal that resides in our world naturally, the temperature, for example, doesn't drop or increase rapidly in the normal climate, unless you have certain system that you are heating and rapidly cooling. Then yes, maybe you would use auto sampling, and even for that, you should do the manual, but fast enough to catch these changes. My bottom line here is you should always use manual sampling. And that's what we make here. So if you use manual sampling, then originally you make the done equal to 0. You didn't do anything yet, so it's 0. And the sampling is 0 and the manual is 0. So here the sampling is manual, and right now I'm not sampling. And since I'm not sampling, there is nothing done. So originally these are the values. Now we find this in hexadecimal. This is bit 0, 1, and 2. So you have 0, 0, 0. I'm writing down in binary. 3, 4 are not there. They are actually unimplemented, so they are 0. From 5 to 7, you have 1, 1, 1. 8 and 9 is 0, 0. And the bit number 10 is actually 1. And 11, 12, 13, they are not implemented. And at the end, you have bit number 15 is equal to 0. So right now, the analog to digital converter is off. And this is what we have, 0, E, 4, 0. And that's what we write down here. That's for the control register. So you need to work it out. But remember, this is actually, this part here, the first part, usually it's 0. Because you usually use a manual sample. Now for the control register number 3, since no choices are made for finding the TAD or the sampling time, there is nothing specified. We will use the easy choice, which is the internal RC clock. And the auto sample, we can choose any value of n. We chose the maximum to give it enough time. Remember, it's mechanical. Let's give it as maximum as possible. And we chose 31 clock. Since we use internal RC clock, we make this one. And since we have 31 clocks, we make this the maximum value, which is 1, 1, 1, 1, 1. And for this one, we didn't use anything from the FOC or FCY. We didn't do anything related to that, and this is not used, so we make them zeros. And this is why we have 0, 0, and for this one, we'll have F, and we have one bit here, which is bit 12. Bit 12 is 1. 13 and 14 are not used, and the last or the most significant bit is 1, and that's 9. Now, once you configure this special function registers, these 4 special function register, the only thing that's left is to turn the ADC on. So at the end, you change this bit and you make it 1 this way, AD1 control 1. This is actually a bit of the control register number 1. Dot AD on equal to 1, and that's it. Now you configure the ADC. How to work with it, what to do in the main method. The main method, you should configure port B, since you are using from 0 all the way to 11, that's 12 bits. You make them outputs to output the digital code. And then you call configure ADC1, the one that we just specified, and you make the value here 0, indicating that you are using AN0 as input. Now, all the other applications that we are going to use or show in this talk from now on, we will always use this method for configuration. Remember that we do it this way. If there are changes in your own problem or system that use ADC, you should go back and change the ADC control register. Basically, the change that you might make is here, and probably the channel. And the channel, we even reflect that in the argument, so you don't have to worry about it. The other change may be in the TAD calculation. Now, in the main loop, while one, remember you have manual sampling. You have manual sampling. So you would say the ADC control bits dot done equal to 0. So you start by making this status value equal to 0. So no sampling is done. And then you start doing the first sampling this way. You do the manual sampling by starting using this statement. AD1 control register not 1 bits dot sample equal to 1. So it's like giving the indication for the ADC load to start sampling. We know that the conversion done automatic, so we don't have to worry about it. What we do after setting this bit, we wait until the sampling is done. How to wait? We check whatever we reset here. So at the beginning, we reset that value, and then we check the while loop. Is it done? Is the sampling done? Is the, not only the sampling, is the conversion completely? Meaning sampling and hold. Both are done or not. If they are not done, equal to 0, still wait or be stuck in this while loop. Once the value is 1, you get out of this and the conversion is done. How to read the value, the digital value? You just read the buffer. You just read the buffer. This buffer, you put it in port P and you show it in the lid. Just to remind you, where is this buffer in the hardware? This buffer is right there. Here. Now, at the beginning of this talk, we had so many mathematics that we need to worry about. You don't see it in the code at all. Why? The ADC take care of it. The ADC take care of it. You don't have to do any calculation, meaning from the analog signal to the digital output. Now let's have more examples to widen your knowledge about this subject. Note that there are always sensors associated with the ADC. Sensor can read many things. Some of them read the temperature, the angle, the humidity. These are just examples. The velocity, so many type of sensors. Now, the job of the sensor is to convert this value, the temperature, you know that the unit of the temperature, degrees centigrade or Fahrenheit. So it convert this value, whatever the type of the value or its unit, to simply electrical voltage that is measured in voltage, V. So usually it has a maximum and a minimum voltage, and whatever value it resides between the minimum and the maximum. Now you have a voltage, and the ADC is ready for it. It takes the voltage, and it generates the binary code. That's the job of the sensor. Now the sensor has some function that maps the real world quantity, such as temperature, to a voltage, and that's its job. This is the definition for the sensor. As easy as possible. This function, it could be linear or none. Now, even if it is non-linear, we kind of estimate it and we make it linear. Now, for the linear function, it is characterized by y equal to mx plus b. And for our case, y is the voltage and x is the real world quantity, like these examples. And you have the slope m and the y-intercept b, or the offset. Here are some examples here. This is y equal to half x plus 2. You can see that the y-intercept is equal to 2. So that's 0, 1, and 2. And the slope is half. So the slope of this red line is actually positive, as you can see here. Now for the second example, here we have a negative slope. So it's moving this way. And the y-intercept is plus 5. And you can see that the y-intercept here is 2, 3, 4, and 5. And there are so many examples that you can imagine. Anyway, we like to work with linear functions. It's easy to deal with. So let's have a sensor example. We choose the temperature. So we have a sensor. You go maybe and look it up in the internet and check a temperature sensor. You will find so many types. Some of them are very precise, some of them are very primitive, and there are so many features for each one of the sensors. The choice that we made here is called LM60, the temperature sensor. You can go and find its data sheet to read more about it. However, the important data for the LM60 is already here. And now this part has 3 pins. You can see them. These are the 3 pins. This is the real LM60 sensor. This is actually a side view of this sensor, as you can see here. One of them is for the VDD. One of them supposed to be for the ground. And the one in the middle is the output of the sensor. So the output, the sensor should convert the temperature, whether it's in degrees centigrade, Fahrenheit, whatever the value of the temperature, it should generate you in the output of the sensor a voltage. And it's generated this way. Now, the leftmost pin is the power supply, or the plus VS, connected to VDD, and the rightmost is the ground, and the middle pin is the V output, or the analog temperature in voltage form. You could connect it this way. That's the VSS. There is a single LE-ion battery cell. It's a battery, and you put the positive side in the VDD, or the plus VS, and the negative side in the ground. And the LM60 will measure the temperature, and it generates the voltage for you. So this device has certain specification. It senses from minus 40 degrees centigrade all the way to 125 degree centigrade. The LM60 output voltage is linearly proportional to Celsius or centigrade temperature, and every least significant bit voltage is actually adding 6.25 millivolt for every degree centigrade. And it has a DC offset of 424 millivolt. So all this information, we plug it in the linear equation. The output voltage of this sensor, we call it V naught or V0, is equal to T, the temperature that you are reading, multiplied by 6.25 millivolt plus 424 millivolt, which is the offset. And you can see this. These are many values that you can test yourself. Plug in the value of T here and try to find the VO. You will find for every temperature the corresponding voltage. So this is the lower bound, the minus 40 degrees centigrade. And the voltage corresponding to that is 0.127 volt. For the maximum or the upper bound, 125 degrees centigrade, that's the voltage associated with it, 1.205 volts. Now, some interesting points, maybe interesting to you, is the freezing temperature, 0 degrees centigrade, which is this value, that's the offset, and 100 degrees centigrade for the boiling temperature, 1.049 volt. So you just put in the sensor and it gives you the voltage, this voltage right there, ready for the ADC. Now, next, we continue this table. We already find the temperature and the VO or the V naught based on this equation. Now, it's the job of the ADC to convert this V naught to a digital code. We call this digital code, for this, we make a choice here to use 10 bits, and we called it R10. We know that the ADC will generate this for us in the buffer. We don't have to do the calculation for it in the code, but we know the mathematics behind it. So the R10 is equal to the ratio of the analog input, the VO, the one that we found here, divided by the VREF, multiplies by 2 to the power of 10, since we use 10 bits. Now, if we know that the VREF for the BIC24 is 3.3 volt, and this is the choice for the reference voltage, then the R10, if you want to calculate it, it would be 131.57 plus T, or this temperature, times 1.939. How did we find this? We just plug in this value, the value of the V naught, right here. And we did the calculation. We know the VREF, we know what is 2 to the power of 10, that's 1024. And we know the other, the slope and the y-intercepts of the analog temperature. We plug in, we do some mathematical manipulation, and we found out this value. Now, you notice here that you have fractions. So to be able to work with that, and you will see this obviously in one of the examples, we will actually try to find the temperature value in one side and all of the rest in the other side. So the temperature, if you want finding the, if you have the R10 and you want to find the digital temperature value, it should be equal to whatever you have here, the analog temperature. Maybe you measure it using one of the tools. This is an analog tool, and you can find out exactly the temperature. And you could compare it to the digital value that you got if you plug in this relation. It should be the same or very, very close. Remember, we are digitizing and we might lose some values. So here we have fractions. What we did, we say that T on one side is equal to R10 minus 1, this value here, divided by this value. And now we multiplied by 1,000, both the numerator and the denominator. So here you would have this value. Notice that we round the value here. And here we get rid of the dots. So it's 1913. Notice here also that we make choices here. We use 10 bits. If you use 12 bits, you can do the same calculation and you will end up with this equation. Let's have an example to understand this. So let's suppose that you have an LM60 temperature sensor that produces 6.25 millivolt for every degree centigrade. We know that this is the slope and has the DC offset, so that's the y-intercept. We know the equation. Using a 10-bit ADC, and we already calculate that, with the reference voltage 3.3 volt, what is the ADC code value for this temperature? So that's the requirements. For minus 10 degrees centigrade, what is the ADC code for it? I calculate in the two ways. One of the easy ways is to do it in 2 steps. First, you convert the temperature to voltage. So you plug in the equation, the one that we No, for the LM60 temperature sensor. You plug in the value T, which is -10. You calculate it and you found the voltage corresponding to -10. Now we know the voltage. The sensor job is done. You get the temperature and you found the voltage corresponding to the temperature. Next, you work the ADC. We know the equation of the ADC. You plug in the voltage, which is this voltage here. We know that the VREF is 3.3 and 2 to the power of 10. Actually, this one is actually 2 to the power of 10, not 210. And you calculate it, it will be 112. In the same way, you could actually use the equation that we found in the previous slide directly, and you plug in the temperature -10 here, and you will get the same result as well. Personally, I like to do it in 2 steps to see every hardware what is the value generated from it. Now, another example. Here it's asked to design a system that reads analog input from the LM60 temperature sensor, then display the temperature in an 8-bit number using LEDs. So you need a binary value there. Same specification. That's the LM60. We talked about this. Now we will have the interface. You can see that this is similar to the schematic diagram for the first example, where we have the potentiometer here. It was connected to AN0. The only difference here is now we are connecting the LM60 temperature sensor in AN0. And instead of using from 0 all the way to 11, now we are using only 8 bits for this, only 8 bits. Since we use 8 bits, we have to use the R10 equation or 10 bits resolution. Now, let's see what to do with the coding. We did the interface, so we need to do the coding next. In the coding, we called configure port B output. So we configure the port B from bit 0 to bit 8 as output, and we discussed this in the GPIO previously. We call configure ADC1 and we give it AN0. We already did that in one of the previous slides in this talk. And then we go through this while loop. Now it's very similar to the while loop that we checked for the previous example, meaning, just so I refer to the correct slide so you don't get confused. Same as this while loop. We have the ADC and we configure it this way. It's configured this way. And in the while loop, we use done, sample, and you wait for the done to become 1, and then you read the buffer. That's what we did in that example. Here we will do the same. Done, sample, wait in the while loop, and then read the buffer. That's exactly what we've done. However, we need one more step to move from this value, R10, to the digital temperature. Now, R10 is actually the AD reading that we defined here. Now, you take the AD reading and you plug in the AD reading in this equation. And now you understand why we multiplied by 1,000, because we don't have floating point or double types in the BIC24 code. So you plug in the value of the AD reading and you find the temperature. This is why we've defined the temperature here. And once you have this value, you actually put it in port B. You can take out actually the temperature and directly put this into port B. But we just specified to make it easy to understand. That's basically the idea using the temperature sensor. Any other sensors, you need to understand the sensor, work out the equations, and do the same thing. The only difference is the jump from here to here. So if you don't care about this and you just care about the value in the buffer, then you're done. You don't have to present the temperature. Since the requirement was to generate the temperature value in the lids, then you need to do this step. Now for one last example, here you have an AD converter module, which is configured this way. You are giving the code, and the configuration is right there, as you can see. And you also have the while loop. This is in the main code, all of this. Y1, you have the sample. You just move the done here. It doesn't matter. You put it there or there, it's fine. Usually, I like to put it right there. Done sample, wait for this done to become 1, and then plug in the value of the buffer of the ADC into port B. This is supposed to be port B. Now from this, we will just plug in the value in the table to understand them better. We know this 0, so the sampling is manual. Here we have here E, so it's actually bit number 3 and 4. They are 0, 0. So here we have 0, 0, 0, 0. That's bit 0, 1, 2, and 3. Bit 4 is 0. And bit 5, 6, 7 is 1, 1, 1. So now we have auto-convert. We know that we have auto-convert. Continue. The rest are zeros. So everything here is 0. From that, we know that we choose 10 bits. And the form is actually unsigned, 0, 0. And currently, the ADC is off. Control register is 0, we know that. The control number 3 is 00E9. And here, there is a slight difference. The values here are zeros. They are actually not used. But instead of having 31, as you see in the previous example, now we have 30. We have only 30 in the SAMC value. And we use the internal clock of the analog to digital converter, which has TAD equal to 250 nanoseconds. And now we understand the code. We understand the special function registers here. Also, you need to know that here, since you have this statement, you are using AN1. We're trying to understand this code. We don't know what's the requirement yet. Now, for this code, it was required to answer the following. What is the total time for one AD reading, which is the sample and the conversion, and you should show your work. Second, if the analog input value is 2 volt, what is the corresponding value of the ADC1 buffer 0? And we know this from the mathematical equation. We can find out exactly what is it. What is the chip pin number? And here you have to be careful. We want the chip pin number of the analog input pin. So basically, where to plug in the analog input. To answer these questions, for the first one, we discussed this actually, and we said we'll use 10 bits, and we will use TAD 250 nanosecond, and the SAMC value is this value, which corresponds to 30 TAD. And from these 3 informations, these are actually the details for them. We know that the total time would be the sampling time, which is 30 here. You get this 30, we put it here. The number of bits, we choose 10, that's 10. And we add 2 more overhead cycles, and we multiply the total by the value of the TAD, and the value of the TAD, since we choose ADRC is equal to 1, is going to be 250 nanosecond, and you can calculate it, and you found that it is 10.5 microsecond. That's the first requirement. Second, since the VDD, since we are using the PIC24 microcontroller, the VDD is 3.3 voltage. The high reference is 3.3, and the low is 0 volt. That's our assumption, and it's shown in the code by having the control register number 2, 0x0000. So these are the choices. The mode is 10 bits. We know that. And from that, I can say that the buffer value or the digital code is actually 2 to the power of 10, which is 1024, multiplied by the ratio of the voltage. The input that we were asked about is 2 volt. That was in the question. That's the input, 2 volt. And the reference voltage, we know that is 3.3, since this is big 24. And from that, we know that the buffer value, after you calculate this, is 621. Now for the bin number, we used AN1, and we know it from this statement. Now, if you go and check for AN1, you will find AN1, this is AN9, 10, 11, and 12 in the right-hand side of the big 24. And in the left-hand side, we have AN1 right there. And this is bin number 3. So this is the bin number 3 chip. Now, at this point, we finished discussing the analog to digital converter. And also, we reached to the last point that we want to discuss in the whole course. I hope you understand the idea of the microcontrollers. Basically, what we said, it's a CPU with its own memory for both the data and the code, and also surrounding modules. We discuss many of them essential modules, like the timer, the output compare, the GPIO, the oscillator module, the configuration bits. We discuss also the interrupts. We've worked with communication modules like the UART and the SPI. And we also discussed the analog to digital conversion today. So this will mark the end of this class, and I will see you in other classes.